I swear I thought I pressed record at the beginning.
That's
Maybe.
what I
What's that?
saw. That's what I saw. That thing. Yeah.
Yeah. I wonder when it stopped recording, or if it recorded at all.
Technology.
Yeah. The second one is treating density as the density as a parameter and omega as a parameter. And so I'm going to call this the state space parameterization. So it's the history of that name is that a state space model is treating the state, in this case density, as a parameter. So if you treat delta t as a parameter, then essentially you have to define a distribution for delta t. Well, there's a bunch of ways you can do it actually, but in this case I'm going to define a distribution for delta t, given a prediction for delta t in every year. In that prediction is just assembled from the parameter the year before, and the deterministic part of the model, or like the rest of the model, I guess. So in this case, this is the equation that we saw before, except without the epsilon. And so this is the prediction of delta t in a given year without accounting for spatiotemporal variation. And then we take that delta t and put it on the right-hand side of the multivariate normal. It's the mean of multivariate normal down there. So does anybody want to talk more about these two parameterizations? Another way you could do it technically is you could calculate what I'm calling delta prime t, or delta star t, or whatever you want to call it. And then you could calculate epsilon t as the difference between dt and d prime t, and then say that epsilon on the left-hand side has a multivariate normal with mean 0, and that would be equivalent to this dispersion for all computational purposes.
Can you say that again?
So another way you could have written this out, if it would be essentially identical, is saying epsilon epsilon t s equals d s minus d s, and then down here have that and this. And so this, maybe I'll put this on another slide so that you can look at it later if you're second version.
Wait, so why parameterize it this way then, the previous ways?
Honestly, I forget why I set this up. I mean, this, I always want to have multiple parameterizations to show, partly just for the purposes of the class, but in terms of why you would a priori assume that one or the other works better, well, just give me a second to finish this notation before I go off on a different tangent. So I predicted spatiotemporal variation. In terms of why you would want the state space parameterization, the state space parameterization in other models will end up being often more sparse, is the short answer. So if you, in this case, oh man, why is that? I was getting confused when I was talking with Elizabeth about this, and now I've confused myself. So, in some models, particularly in nonlinear models, like if we replace the Gompertz model with a Ricker model in this case, then I'm pretty sure the state space model would be way more efficient. And the reason for that is that in this case, if you make a small change in epsilon in the first year, it affects density in year t+1, which affects density in year t+2, which affects density in year t+3. And so, a small change in epsilon will affect the probability, the gradient of the probability for all subsequent years in general. In this linear case, it doesn't matter because it all kind of balances out. But in a nonlinear model, the innovations parameterization ends up dense. Because for this reason, I'm trying to say where epsilon affects all subsequent years density and therefore epsilon in the future. That's the way that's intuitive for me to think about it. If that's not intuitive and people want to keep talking about it, let's do so.
Yeah, let's do it again.
Okay, so let's see how do you explain it. Explain it again. So.
Do it again, Jim.
Yeah, I know, exactly. Yeah, I mean, I actually think the mystery is how these are so similar in the mystery. What's not intuitive to me is that both of these end up so similar in terms of sparseness in TMB. And that's sort of the magic of how TMB is doing this sparseness detection. So in this particular model, if you change epsilon in year t, the first year, it kind of propagates forward in time into densities, but because it's a linear model, it doesn't really matter that much.
Linear as in you're at, like, the dt sub t minus 1 is added on to the other terms in the model.
Yeah, exactly. And the only effect of a change in t, so if epsilon in year t, the first year affects density into the next year, that change only propagates through via this linear effect rho. But if you've got a nonlinear function for this, like a Ricker, suddenly a small change in epsilon is going to change this, and so it's going to change the prediction of density the next year, which affects the prediction of density the next year after that, and the next year after that. And so suddenly a small change in epsilon is affecting density for all subsequent years, which means that it affects the probability of process errors in those future years too. Whereas in this linear one, where the effect of density is propagated forward through just this rho parameter, if you increase epsilon in a given year, the partial correlation is 0 for non-adjacent years, because the action of changing epsilon in year t, it affects epsilon in year t+1, but given that effect in year t+1, it has no further effect, which is what the partial correlation represents.
I won't be offended if you say this is crazy, because I still didn't really totally understand the whole Kronecker thing, but like to put that in that terms, is, for example, like the first one where you have two multivariate normals the same as if you had one multivariate normal, but with like the Kronecker product with the two correlation matrices instead, or some.
Well, exactly. It would be and we could write that out.
I guess when you were presenting that, I was thinking like, oh, if you wanted to go into more than 2 dimensions, you have to do this Kronecker product thing. But it looks like you just actually split those two pieces out, even though they're not independent. you split it onto like one time
Totally.
and then one space and time.
Yeah, so if, to kind of explain this, I have to kind of write some notation, and so, hang with me while I.
If you do backslash and then the name of like epsilon or whatever, it'll just show up.
Okay.
It's like the greatest little thing ever in PowerPoint. Yeah.
Except I never remember what they're called, I just only know what they look like. So I'm gonna use upsilon for the net effect of spatial and spatiotemporal. And, let's see, and we had omega before, I'm kind of assuming that I got the math right before. Product or product. I plus this. So the other way you could write it is this. And you were on the right track. You were just missing this sort of spatial and spatiotemporal thing happening simultaneously. So, and I'm sorry, this isn't a W matrix. This is a one matrix. So a matrix of ones. So the spatial process, the vec of U has the same, U is this matrix with the same shape as the spatiotemporal process. It's the matrix is the number of sites by the number of years. And so you take the vec and it needs to have sites by years as the dimensionality. And that's the dimensionality of this spatial correlation chronicled by the temporal correlation matrix. And if you're going to add it, this also needs the same dimensionality. So that's, so you've got this hint that you need this one matrix. You can't just do a matrix of one dimensionality plus a matrix of a different dimensionality. That's just not defined.
Wait, is it dimensions space number of sites times number of times, or just number of spaces in columns and number of times in rows?
So U is U is a matrix with number of sites in rows and number of times in columns, and when you vec it, it's just taking the columns and stacking up into a vector with length equal to number of sites times the number of years.
Okay.
And so on the right-hand side, the covariance matrix needs to be the number of sites times the number of years by the number of sites times the number of years.
Okay, that's
That's what you get when you take the Kronecker product of the spatial correlation matrix and the temporal correlation matrix.
And the number of sites in this
Sorry.
case, because it's like not evenly matched, is the number of longitudes times the number of latitudes.
Sorry, I realized that I was missing some additional change in notation. So just give me a second here. Where the candelabra thing. I had an old lab mate who commented that you've got some fancy math when you start having to use the candelabra. That stuck with me. So we're defining this new phi. Is that what that, or is psi?
Psi, capital Psi, I think, right?
Is that a capital? I meant for it to be lowercase.
I'm pretty sure it's capital Psi.
I think it's just a, oh geez.
Parsa?
So I think the capital looks slightly different. Well, that according to word editor, that's a lowercase.
Okay.
And so we're defining a new random effect that is the net effect of spatial and spatiotemporal. And we can get that from an additive covariance function. So like next week in the multivariate stuff, we're going to talk about additive covariance matrices again. If you have a valid covariance matrix A and a valid covariance matrix B, then adding them together is also guaranteed to be valid. So in this case, this is the spatial covariance, but then chronicled out to be across space and time. And it makes sense that it's going to ones because it's perfectly correlated across times. So the spatial effect is not varying over time. So the spatial effect at site 1 and time 1 is identical to the spatial effect at site 1 and time 2 and time 3 and so forth. And then this part is kind of what we've talked about before.
And in this case, you're kind of treating like space as one-dimensional, right? Because there's not, are you just like, is it like actual distances in this?
It could be any spatial matrix. So in the model we're using in the code, it's not one-dimensional. It's this two-dimensional function. But if we've got 1,000 sites, we've got 1,000 by 1,000 covariance matrix that we're generating from the distances between them. So like you can always sort of, I'm using that RF Gauss function to kind of disguise that some of those intervening steps, but you can always take, log xy is this 1,000 by 1,000 matrix, but that's a little bit too big to be worth looking at. But like a 50 by 50 matrix, you can always calculate the distances between them using the dist function. It'll just give you the distance between those points. And then that distance function is what you put into it, a correlation function to calculate the correlation between those points. Okay, so any further thoughts at this point? So we've looked at the two parameterizations. The point of this was to confirm that there's sort of two parameterizations, which we've now expanded to kind of like three parameterizations, and if we're different notation for those parameterizations or something. So now I'm just going to run them, and we can look at the code in a second. So the first one that I'm calling states as random, or the state space parameterization. Wait, actually the notation is exactly the opposite. So this is a mess up on my part. I should relabel version 0. But this first one is the states as random, or the state space parameterization. So like in earlier weeks, we were referring to them as sweep upstream to downstream, and that was version 0 in earlier weeks. And version 3 was the joint, defining the joint probability using built-in functions in TMB. And now I'm introducing a new vocabulary in this class, the innovations versus state space, because I think that's easier, kind of more intuitive, and also probably more terminology that other people use outside this class. And so the sweeping upstream to downstream through time is sort of a state space parameterization of it. And the joint version using TMB functions is the innovations parameterization. If we run them both, they give very similar parameter values. So in this case, the true spatial scale is 0.1. And the estimated range is 0.13. The range, I'm pretty sure, is twice this. The range, as I refer to it, the distance of 10% correlation, is, I'm pretty sure, twice what the random fields package defines as the scale. So in this case, we're underestimating the decorrelation distance a little bit. Sigma O is estimated at 0.37 or 0.35. These two different versions give slightly different answers because of boundary effects again. So I'm not bothering to correct for the temporal boundary effects that are arising. But they give very similar values of phi, similar values of rho, and then just small differences in the variances as you'd expect with boundary effects. And they're giving kind of qualitatively pretty correct answers in terms of, sigma E being close to sigma E, sigma O being close to true value. In terms of the sparseness, as I said, that the state space parameterization in this case is slightly less sparse than the innovations parameterization, which is sort of surprising to me. in general, the state space will be more sparse than the innovations. And not in general, but often it will be more sparse for, in particular for nonlinear models. So by default, I often start with a state space parameterization, and that instinct would be wrong in this case. And then if you look at the Hessian, you can see why that innovations parameterization using built-in D&D functions is slightly faster because it's just more sparse in this case. Or no, you can see the sparseness. We haven't looked at speed yet, actually. So in this case, it's so weird. The cross correlation between the spatial part and the spatiotemporal part, the cross partial correlation is more sparse in the innovations parameterization than the state space parameterization. So all these block diagonal parts are the same, and it's block diagonal because this is essentially a visualization of that Kronecker product psi that we were looking at a second ago, where well, it's not quite that actually. I'm sorry, but it's this part is the visualization of psi that we were looking at before, where you've got a Kronecker, the partial correlation across time is this tridiagonal, or it's sort of diagonal plus one above and one below. So the partial correlation across time is a first order adjacency. And then the spatial block is this sort of confusing, kind of dense looking, kind of partially, sort of sparse, sort of dense kind of looking thing that we'd have to dig into to really get the intuition about.
Have you looked at how the parameter estimates change whether or not your mesh is refined or not?
No, not really. And that's, so like Curry Cunningham has been doing explorations that for NOAA. And this woman, Laura Trombley Mayer, who's now with Dragonfly Consulting, has been doing that a bit. But it's not something I ever really explored in any formal way. If people are interested, I'd love to. I think both of those people are doing it in a very applied sense, like putting it fast and seeing kind of what effect it has. And, it'd be nice just kind of from a theory perspective, kind of look at kind of standard simple models and see how much it matters. And then finally, in terms of runtime, in this case, the innovations parameterization is also about twice as fast, so it matches the sort of the more sparse model is also faster. I was doing some explorations earlier, and that wasn't the case. But in the scheme of things, being twice as fast is not really a big deal. I mean, like you need kind of 10 orders of magnitude before it's really going to qualitatively change. An order of 10 times or an order of magnitude before it's really going to change what you can accomplish. I think.
Unless you're running it millions of times.
I mean, you can always just get twice as much computing power from Amazon. It's just more expensive. I just think like you can get qualitatively different models when you get an order of magnitude speed up. That's sort of my personal rule. It certainly sucks to be the grad student who has to farm it out to twice as many computers on the lab or whatever. Anyway, so that's the kind of runtime comparison, and then in terms of looking at the code, I think I'll only look through maybe I'll look through the states as written. Any preference, the state space or the innovations parameterization? Which one to look at? I think the state space is maybe a little more intuitive. So we got the same isNA function at the top. We're defining, reading in stuff. The SPDE method reads in these three matrices. I hope everybody's kind of caught up to that level. And then we've got, the mean of this Gompertz model. We've got phi, the offset. We've got two different taus, where tau scales the standard deviation. We've got a single kappa, because I've gotten in the habit of sort of wanting that Kronecker, that it's kind of nice. I mean, it's just easier to interpret if the spatial scale is the same between the spatial and spatiotemporal process in some class of models. And then rho is the autocorrelation, controls density dependence. We've got the random effects, bookkeeping, and then this block of code people still probably aren't used to seeing, but I'm taking log kappa and calculating kappa squared and kappa to the fourth power. When I started doing these models, I didn't know that m pi is just pi in C++. And then range is, maybe that's even more confusing though. I'll go back to that just a second. The range of this SPDE method, the distance of 10% correlations, is defined as the square root of 8 divided by kappa. That's just from the original paper. And then the standard deviations have this formula that's also from the paper, and I don't have any real intuition about it, except that kappa is the decorrelation rate. And so it makes sense that as the decorrelation rate goes up, the distance at which it decorrelates goes down. And if you have a decorrelation rate going up for a fixed variance per distance, which is the interpretation of tau, well, I guess it's the inverse of the variance per distance. It's the precision by distance, which doesn't mean anything. Well, anyway, these formulas are just something you look up. And then you assemble this sparse matrix, Q, and it's really important to define it as a sparse matrix so that C++, I mean, these are being fed in, the G0, G1, G2 are being fed in as sparse matrices, but you need to make sure that your intermediate calculations are also using sparse matrices, using that eigen : sparse matrix form of type. I'm passing in alpha is a vector of fixed effects representing kind of density covariance, and in this case, xp is the density covariance, and I'm just going to put in xp as a column matrix of ones, so an intercept. I then do the calculation of the equilibrium that only holds if rho is between -1 and 1. And then I calculate this linear predictor for log density, doing this recursive formula. I put in the probability of the random effects using this sort of TMB notation. So I've got a Gaussian Markov random field with precision matrix Q that I rescale to have log tau O variant. Well, I rescale with that log tau O, and that means that it has a standard deviation equal to what I calculated above. And because of the way these functions are defined, it's returning a function, and so omega x has to be passed to a function that's outputted by these other functions. And then similarly here, I loop through time and compare my my state as being treated as a parameter with my prediction given the state the year before. That difference has a multivariate normal distribution that follows this Gaussian Markov random field. So any, in this case, this is probably the, the block of code that people, have been hopefully learning in weeks 5, 6, and 7, but it's still maybe unfamiliar. Any questions about it this time? The fact that you have to rescale the precision matrix with this, the inverse of tau, is again just sort of the way that Inlet defined these parameters originally, and I'm using sort of the Inlet parameterization So you kind of just have to take that, take my word for it, but that's how you generate a endless style Gaussian Markov random field.
What's the line 83 at that end? I heard you explain it, but I didn't catch it quite. The
Yeah,
log
so this-
EXT dot cool.
This is going to be the vector, this is going to be a vector of something governing the random, the distribution of delta, or of D, which is treated as a random effect. I mean, all random effects need a distribution. So we know that we need D to have some spatial probability distribution somewhere. And in this case, we're using this parameterization, this state space parameterization, where we predict density without the epsilon piece. We then calculate epsilon as the difference between the state in a year and the prediction of the state given the previous year. And then we put that epsilon in as multivariate normal. And so that's identical to what I'm doing here, except I'm not just defining epsilon equal to this, I'm just putting that difference directly into the function. That might be slightly easier to read if I actually type it out, so maybe I'll just take a second to do that. T. I'm hoping this will work in the file. Mess it up. So maybe that's a little easier to read, but
So you predict, you have the spatial temporal prediction D for every space time, and then you have the spatial temporal D prediction for every space time given the surrounding space. Is that what those two things are? Yeah.
not exactly. So D sub xt is a parameter. So in a state space parameterization, the state is being treated as a parameter. And so I'm defining log D sub xt up there. Okay, and that's what I'm doing down here, log dxt. And then I'm defining the prediction of log dxt, and that prediction of log dxt is just a recursive formula given the last year, or in the first year, it's just defined for the equilibrium. So it's the same equations as we used in the other way, except just without epsilon in it.
Okay, is that like analogous to like just initializing again? Here.
Well, so this line is initializing it. So you could, basically, this is algebraically identical to the other model. The big picture point is that this is algebraically identical to the other model. You could just start doing algebra and you can get the other model. The only difference is that one of them treats D as the random effect, and one of them treats epsilon as the random effect. And then it just calculates, the one where D is the parameter calculates epsilon, then has a distribution for that. The one that where epsilon is the parameter calculates the distribution for epsilon, and it calculates D from that. They both get you to the same place.
Mm-hmm.
But it matters because TMB is doing the inner, it's doing the inner optimization on the parameters. And so if you reparameterize the model, that inner optimizing might be more efficient because it's more sparse or because it's more close to quadratic or whatever. So that's the big picture reason for it. But are you asking about sort of like the algebra that is required to get to the?
No, I think I understand it now.
So, for the sake of time, I might skip showing the other, the innovations parameterization, but people are free to look at it. It's essentially identical code, except it defines the joint probability of epsilon, and then it calculates the expected catch rates from omega and epsilon. And I'm not going to walk through it in detail. I think that we've been doing this for a while, so why don't we take a break? How long do people want to take for a break?
At least 5 minutes.
I'd love a 10-minute break just to go to Agua Verde and get some food.
That sounds reasonable.
Okay, so people off site will be back by 11:45 or maybe a couple minutes later. 11:50 or 10:50 for sure. I'm gonna start talking maybe a little bit earlier. I'm afraid I'll get hangry. At different times we've talked about sort of different strategies to scale up your model, and this is sort of the best kind of set of advice I could ever come up with. You know, the most obvious one is make sure your model is as good as it can be for your task. So, you know, in some cases that means developing multiple versions and testing it on the types of data that you have, because of course the sparseness of a model governs how fast it runs to a large extent. And sparseness depends not just on the distribution of your random effects, but also on where you have data or don't have data. So a model that can run efficiently with a certain spatial pattern of data might run differently for a very different pattern. So, you know, check sparseness is the #1 way of scaling up a model. I also, you know, work in an arena where we want to make sure that we are unbiased in these sort of derived quantities, and so we end up using bias correction all the time. And a big breakthrough for us is this new feature that allows you to bias correct some variables and not others. And that's available in this bias correct control input to SD report.
Why wouldn't you want to bias correct all of them?
Because it's super, so it has different sparseness, basically. So you can have a sparse model, but then have a derived quantity that's super dense, and it'll just blow up the whole model. There's also a new trick that we have recently been figuring out when it's useful, which is Gaussian Markov random fields have the probability, evaluating the probability density function of them involves both this sort of sandwich product of the vector of random effects times that precision matrix, but it also involves calculating the determinant of the precision matrix. And the precision matrix is made up, it's generated entirely from fixed effects. And so you only ever need to evaluate that determinant when doing the outer optimization. You can do the inner optimization, which involves this. You can do the inner optimization and evaluate the probability of the GMRF just by taking that sandwich product and not dealing with the determinant at all. And so Casper has put in this neat feature where you can build a model that does the full probability density function calculation only when doing the outer optimizer. And when you're doing the inner optimizer, it saves time by only doing half of the evaluation of the GMRF probability. So you can get some good speed ups using this sort of Gaussian Markov random field models, using this new feature that I'm not really going to go into details about, but if people want to talk about it more, we can. So these are all kind of modeling techniques. I guess another one is choose a new approximation to your dynamical process. So, you can always have a spatial model. Like, for instance, we're doing all these spatial models where we, people used to do like spherical or Gaussian correlation functions, and we're approximating all as a Matarin because that's more sparse. If you want to, you could use a Matarin that instead of has second order adjacency, has first order adjacency, which is not what Inlet typically does, but it's about twice as fast. And I'm not going to go into details about why Inlet does do it. But you can always kind of explore new approximations to your process that make a model run faster. So anyway, after you make sure your model is optimized, then you go out and buy a computer, and this is sort of like what the FuntLab used to do. I think a lot, like to make big models work, is just like farm stuff out on the lab, or these days like labs with money, you just do Amazon Cloud Computing to scale stuff up. You can also decrease your spatial or temporal resolution. So, already, defining these models in sort of a predictive process formulation where you define a number of knots. You don't optimize for the number of knots. You just pre-specify it as a way of improving computational efficiency. And then there are, geostatisticians back in the day used to do these like runs and batches, and it's sort of something we're trying to move away from. But ultimately, if you have a really big model, maybe you run a batch model on North America, and a separate model on South America, and a separate model on each continent, instead of trying to run a full global model for something. I don't know if you guys in the spatial models that are in theory replacing the global burden of disease maps to build in spatial covariances. Are those being done kind of continent by continent or globally? Or?
They've only done Africa, so I think they're trying to expand it.
Yeah.
I'm not sure.
Yeah. Okay. Yeah. So presumably they'll have a choice of like if they do Africa, do they want to model it jointly with Asia and Europe just to look at like where the Rock of Gibraltar maybe has some disease transmission, and maybe there's like an adjacency transmission through Israel and the Sinai Peninsula or something. So those are the strategies for scaling up. And then finally, the exercise that I was hoping we would get to is first for people to run the class code, then to extract the estimated for either of these models. So let's just pick the states as random. There's report out the log d xt, the predicted density, which it's already being reported out, and then visualize that on a map at the spatial resolution that the estimation model is using, and compare that density map with the density map from the simulation model. And then I'd like people to just do some kind of informal exploration of how the comparison of the kind of downscale, the fine scale versus coarse scale, how that changes when you change the number of stations in the operating model and the number of knots used in the estimation model. So just kind of informally do a little bit of what Caitlin, you were asking about, sort of like how specifying the number of knots. Maybe you actually asked about specifying the mesh, but you could look at that too if you wanted. But I'm hoping in 20 minutes when the class is done, we can spend about 15 minutes here until about 11:10 for people making the visualization code for the estimation model output, and then spend about 5 minutes exploring that, and then we can spend 5 or 10 minutes talking as a class about what insights we'll gain. So is that clear, marching orders? Are you ready? Okay.
John. Look at that image. My perception is with the spatial sample one, it's just like, I'm kind of imagining it as like a stack of these images. Where like each vertex on a triangle is correlated across the stacks, like through the stacks.
I don't think that's how this is parameterized. You can use this method in 3D as well.
Mhm.
But the way, and Jim, correct me if I'm wrong, is this is more of a state space kind of, think of it more as a state space where you have these stacks, but they're related by either the Gompertz plus, by the Gompertz plus an error, not by edges in the actual GMRF representation. That's what this representation.
Yeah, I mean, at the risk of confusing things, just because of the particular structure of the Gompertz, you can think of it as that joint regression where it's, the joint covariance is the Matarin spatial covariance and the Kronecker product of that with the A1D AR1. And so there is like a non-zero correlation between adjacent mesh nodes across time.
Right. But they're only sort of, they're sort of only connected vertically.
Yeah,
They're
that's
not connected to adjacent ones through time.
Yeah,
So I'm thinking of it like a stack of these like triangle meshes, stacked on one another, and they're connected vertically by some correlation, and then.
totally. Yeah, I mean, like maybe if I understand it right, like maybe you're asking like, so there's a guy Breivik who's been doing bycatch modeling where he actually has continuous space, continuous time with different locations in every time period being located. So he has to actually make the mesh in 3D, whereas we're just defining the knots being at the same location every time.
Okay.
Or if you were modeling like a 3D process,
Mhm.
you could do that in the SPDE method and just expand it to a 3D mesh.
But I feel like it.
But they're just different approximations, the
Yeah.
same function, I guess, is my claim. Like,
It's conditionally dependent. Just like, right, like one vertex over and one time spot over.
yeah, the partial correlation goes to 0 in space past second order adjacency. So the partial correlation is non-zero for your neighbor vertex and your neighbor's vertex.
Yeah.
And it's also, the partial correlation is non-zero for your one adjacent times.
Yeah.
And so if you think about it, if you do the Kronecker product, you're a vertex that's one time away and one vertex away has a partial correlation that's non-zero.
Cool.
And in fact, a vertex that's one time away and two away also has a non-zero partial correlation.
Okay. So. Right. Makes sense. So then why do it in that 3D sense? So it just has that one step.
Yeah, I mean, because you can, like, on the one hand, it might be more efficient. If you've only got 10 points that are each in, but, continuous space, continuous time. My way, doing discretizing time, you might have to, even if you have an unequally spaced AR process across time, you'd need 10 spatial fields, one for each time period.
Mhm.
And so you'd end up with 100 random effects, if you're following me, because you'd have a mesh that's like at minimum 10 spatial locations. You'd have to do that 10 times.
Yeah.
Whereas the 3D mesh version, you can just have 10 random effects at minimum.
Mhm.
So I think there's maybe some computational benefit in some instances of doing the 3D mesh smoother versus the. I think for separable models, it really doesn't matter very much. I think you get into kind of mildly non-separable models, like where the Kronecker product is not an expression of the joint covariance, and those get messy.
Yeah, but you can express different relationships more effectively. Like if you have, as an example, if you have something where a certain distance at time 0 is not very correlated.
Mhm.
But then after some time, if it's like a diffusion process, after some time, then at this distance and some time lag is actually going to be fairly correlated because of that diffusion process,
Got it.
rather than sort of both decreasing at the same. Yeah, it's fairly limiting.
Yeah. We'll briefly hit on sort of like separable diffusion approximations in
Yeah.
9.
It was sort of what I was trying to ask, I think, earlier, is like the way that these are parameterized here is you can't have the anisotropy, say that word right, in space. It, like,
No, you could.
really with a,
Yeah.
then you can have separate, because the way I was seeing it was like, it was just distance between two things, and you weren't really taking into account the, like, is it distance this way or this way?
Exactly. So the code I'm showing here, again, for simplicity, I'm just going back to the isotropy. I say you say
Isotropy.
isotropy. Isotropy. I'll
I don't think I've ever heard that word before. So isotropy, or in this
well, I don't know.
Esotropy. It's just fun with everyone.
Yeah. Like anisotropy, anisotropy. I don't. Yeah,
That's how I say it in my head.
yeah. I'm gonna just for now. I'm gonna stick with, so I don't confuse myself. I'm gonna stick with my wrong pronunciation. But you could change these models to have geometric anisotropy, and all that would take is substituting this formula for Q with a different block of code. So this Q is the spatial correlative precision matrix, and you just have to use a different version of that. And I worked with Hans Skaug, so there's actually an object that just reads in all of the stuff you need from INLA to do the geometric anisotropy. It's bundled as a thing called like SPDE and ISO that you just read in an object. It's properly formatted, and the directions are on the TMB website. So I'd be happy to walk through the details sometime if you're interested.
Yeah, I mean, I don't know what the extent of my project is going to be. I feel like I usually like think of the most ambitious thing I can do, and then I'm actually doing something much less ambitious.
Totally.
But I would like to try it potentially. I don't know.
Yeah, I'm trying to think. You guys know Neil?
Yeah.
So last time he did like a big like Asian space faring smoother or something.
I think it's something similar to what I would like to do.
Yeah, but you can do that. It like the way we're setting it up. It's isotropic in space, like x and y coordinates, but it's a separate decorrelation rate in time.
Yes.
And so it's you can using those 2D AR1 processes, you can have a different decorrelation rate in each of your axes. And if all you're doing is like an age in space model, that's probably enough to get you most of the way there. As a side note, like MGCV, there's no way to specify that you want it. As far as I know, your options are either globally isotropic or a tensor spline. There's no way in MGCV to have it be like isotropic in space and anisotropic in time or something like that. So okay, so we're almost done with the coding block. Does anybody got to the point where they're starting to yield insights on how this changes with different resolutions? How much more time were you guessing? Or here, maybe you might have I come around like over your shoulder.
Sure, I was just playing with the mesh
Okay,
part of
okay.
it. So I'm gonna run it.
Yeah, so it looks like
Version 0. If I can spell. That would be helpful.
And it runs a little slower with it going to terminal. I don't know if there's any way to turn that off in RStudio.
Oh, really?
Yeah, I mean, just because it sucks up computation power printing the screen.
That's good to know. Alright.
In
I think
like-
quiet equals true, right?
Yeah, so you can do it. You can do it on the TMB side. In like a non RStudio R terminal, you can like right click it and say like run print blocks or print continuously. Well, okay. So is anybody going to volunteer to sign into GoToMeeting and show stuff on their screen? John, it looked like you had some interesting stuff to show potentially about that.
I haven't gotten it to fit yet, but I did get that mesh builder to work.
Yeah, could you sign into GoToMeeting and try?
I think I have it installed. Sorry, I'd have to install GoToMeeting, but I can do that.
Yeah.
What's the number?
So what's the number?
To join the GoToMeeting.
Oh, well, it's just a URL. I mean, you don't need to call in.
Sorry, I need the meeting ID number. It's in the URL.
It's this one, I guess, 1149. Can you see my screen here?
Yeah, I can. Thanks. 149-079-25. Yeah, okay. I have your screen now. Become the presenter to start sharing your screen.
For people off site, we're getting John Bass set up to be the presenter because he got the inlet mesh builder, our shiny thing working. So I think that I shared it with you, but you have to like share your screen maybe at the top or something.
Yeah. Yep. Then running.
While you're doing that, I'm just gonna try to finish what
At the end of class, Jim, can you share all of the updated stuff on GitHub?
Yeah, I will for sure.
Thank you.
Well, I crashed my R terminal, so we can go to John's.
Okay. So I've got this.
And can you show the code for how to access the GUI?
Yeah, I can't. It's actually just once you load inlaw, it's just mesh builder, open parentheses, close parentheses. Okay. You don't pass anything to it, and it starts up the Shiny app. So it'll either open it in an RStudio window if you're in RStudio, or in your browser.
Cool. So like library, inlaw, and then oh yeah, but I don't have the right version. But it'd just be mesh builder.
Exactly, just like that.
Yeah.
Yep.
But I don't have
Version
it all.
18 something, I forget, but And then this, what I'm sharing here pops up. And you can go here for the boundary domain points variable names. I'm not quite sure why it's named that. But then you can, so if we go to our original.
We can't.
Huh?
Where's your mouse?
Well,
Oh, that's Jim's mouse. I don't think you can see my mouse
Okay,
for
gotcha.
some reason, unfortunately.
Okay.
I'm not sure why you can't see my mouse, sorry.
It's okay.
Anyways, so you can pick, and these are the actual points that you would get.
and it's just pulling stuff out of your memory.
Yeah, so whatever's
our
in your
side.
global environment will be available. So, or if you just want to play around with it, you can click random and generate some random points and tell it you want, 371 of them or something.
Sure.
And you can play around with how to do that. But if we go back to our original points here, so this is the sort of default mesh that it actually gives you. And it's kind of, obviously, it's a lot finer than what we were getting.
Yeah.
But the important thing is to note that it's got this black border, so it puts an offset around the observation points of a bit, and you can adjust that with this offsets for automatic boundaries on the left side. So if you wanted to bring the inner boundary tighter around the observation points, you would make that value smaller. And then your outer boundary takes care of that inflated variance, the edge effects. So you can kind of adjust that larger or smaller as well. So say we wanted this. And then,
Wait, can you say that over again?
yeah, so you have two parameters for the boundary offsets. So you can have your inner offset be anywhere from basically tracing tracing the outside of your observation point locations, or you can offset it a little bit so it's a little bit larger than those. And then you want an outer boundary that's a fair bit bigger than those to account for the edge effects.
Yeah, and I've heard it sort of, they want 2 times the decorrelation distance is
Yeah.
the rule of thumb I've heard.
So once you set those, you can set your max edges. So from here, we want to go to the kind of display here. Unfortunately, we lose our observation locations, but they're there. And so the next setting is this max.edge. And these set how the maximum length of each of these edges inside, so the smaller one is inside your observation domain, and the larger one is outside so in that outer range. So you don't care about the outer boundary so much because you're mostly doing that just to account for these edge effects. So you can make that sparser and give it a larger edge effect. So if I make that a little bit larger, it doesn't do much.
Sure.
Something like that. But I can make the inner one a fair bit larger, and now it changes a fair bit.
Sure.
And should pop up any minute. So that looks a fair bit different. And it looks like it sort of artificially has small triangles around the edges here, probably because of the way that it's tracing that inner boundary. It sort of needs a vertex at each of those turns.
But at this point, it probably has fewer vertices than the data points, and it's doing the other data points by linear interpolation.
Yeah, exactly. And this is basically uncoupled from where the actual data points are. So if you would have to find some way to get that interpolation. So this, say we liked this, and these max edges are important. You want this is definitely where you want 2.5 to 5 times. These max edge lengths should be your decorrelation distance, or you don't get a good approximation of your spatial field. So say this looks good, and it's sort of a balance of getting something that interpolates well and not getting it so fine that you're estimating, you're making it computationally more difficult than it needs to be. This minimum angle one is another important one. Apparently if your minimum angle is less than 21 degrees, so those real long skinny triangles, there's no guarantee, there are no convergence guarantees on your spatial field. So, if you bring your minimum angle way down, it takes a minute for GoToMeeting to catch up here, but you get these kinds of things. So you want to keep your minimum angle. So in this case, I think the lower minimum angle is for the outer domain, the edge effects, and the inner minimum angle is for the inner domain. And I think it just sort of gives you better properties, basically. I'm not sure what this mesh resolution assessment stuff does, really. It wasn't.
Well, why don't you click active? I'd be curious if it tries to do some assessment based on SE or something. I'd be curious.
No, right now it just errors out.
Okay, that's funny.
There's some file exists. There's no file associated. I don't know.
Yeah, who knows what that means.
If it's working, you can see, for some reason it's not coming up right now, but when it's working, you can actually see this quantity here, that right column on the left side will give you an actual map of what your standard deviations look like, and you can see that.
Wait, what? Can you turn it on, or what did you say?
It's not. First, it hasn't been working for me today.
Okay.
Yeah, we're not quite sure why. Advanced. Maybe if I go fine here. Unfortunately, I haven't been able to get it to work.
That's fine. That's fine.
I've seen it work before, but basically, you see on those outer edge, all the way at the edge, you get the standard deviation goes red and inflates a bunch. And you can also see that your variance is highest at your vertices, because that's what's actually varying, and then lowest sort of in the middle of each triangle.
Yeah, although again, that's just the variance from the prior, not the variance conditional on the data.
Yeah, and due to the approximation,
Totally.
There's some error in there, and I'm not quite sure how they incorporate that exactly.
Yeah.
But you can also go to like correlation here, and sometimes if it's working right, if you click in one location, you can see that it looks like a pretty circular.
Totally.
And you can adjust your smoothness and range on the bottom there on the left.
Cool.
But if you have an overly, if your edge lengths are too long for your correlation range, then you can see that the shape of the correlation isn't round anymore. It's kind of got these weird artifacts due to that.
Yeah, cool. Yeah, and that when you have geometric anisotropy, I mean, you can kind of imagine it being a deformation, like some shrinking of axes or rotation. And you could imagine that in that case, there's like kind of literature about how the finite element placement should depend on that, parameters that geometric anisotropy too, which of course we don't get into, and they don't either, because they never actually built geometric anisotropy into Inlet, as far as I can tell. They just did the math and then never built it. But.
Yeah. Yeah. So that's what this does, and then if you scroll back up, you can actually say, okay, I like how that looks. And then copy and paste this code to get the same mesh in R to use in TND or in Inlet.
Yeah, it's pretty cool. We're over class time, so thanks, John. It's fun to get a chance to learn something. Yeah. So, any last questions before we call it for today? No. Yeah. So next week will be about multivariate models and using the VAST package.